Hello my dears, today we're going to talk about how to read an energy diagram, and basically it's a plot that shows the change in energy that occurred during a chemical reaction. So when a chemical reaction takes place, you have to keep in mind that the reactants will form the products. So the reactants come with a certain amount of energy and the products have a certain amount of energy. Okay, the barrier that the reactants have to overcome to get the reaction started is called the activation energy. Okay, so I'm going to talk to you guys about how to read this plot. Okay, on the y-axis is energy. Okay, we talked about energy. We said it's measured as kilojoules. Okay, and the x-axis, they put reaction coordinate. Sometimes I have also seen it as time. So basically, as time progresses, the reaction is taking place, and this is what happens throughout the reaction. Okay, so the way to kind of think about this is, you are kind of getting your day started. You're kind of, low on energy, and then you have to put in some energy to get dressed, make breakfast, catch your bus, all that. So that's this hump here, is you trying to get your day started. Okay, and then as the day goes on, things kind of go downhill from there, and then you end off on a good place. So you end up as a stable product. Okay, so the reactants are basically right here. This is how our reaction gets going. The activation energy is this barrier that we have to overcome to get the reaction started. Okay, and then the energy of the products is noted by this guy E. And basically, if you have your products are low in energy, that makes them stable. And if they end up maybe like right up here, they have high energy and they're unstable. Okay, so we're going to talk about each letter in basically right now. Okay, so again, A is the energy that the reactants are bringing to the reaction. B is the activation energy. This is the minimum amount of energy required to get the reaction going. C is known as the activated complex, which is an intermediate state that is formed during the conversion of reactants to products. And the activated complex is the structure that results in the maximum energy point along the reaction path. D is the enthalpy of the reaction, and basically you can get it by subtracting the energy of your products minus the energy of your reactants. So basically, if you did E minus A, that would get you D. Okay, so this is delta H. Okay, so let's say, for example, this was 5 kilojoules and this was 20. Okay, so this might help you if you see numbers involved here. And then let's say this guy was 30 up here. Okay, so the energy of the reactants is 20 kilojoules. The activation energy is this top of the slope to kind of where the reactants get started. So that would be 30 minus 20, which is 10 kilojoules. So here the activation energy would be 10. And this is just, the numbers are just a reference point. It's not always 10, it's not always 20. I'm just kind of helping you guys see this. The activated complex is basically from the bottom of the pit to the very high top of the activation energy. So in this case it would be 30. And the delta H of the reaction, again, it's the energy of the products minus the energy of the reactants. So if my products have 5 kilojoules and my reactants are 20 kilojoules, that means my delta H is negative 15 kilojoules. And remember, if your delta H is negative, that indicates that your reaction is exothermic. Okay? And then E is the energy of the products. That's basically where it hits. So my example here was that it was 5 kilojoules. Okay? So energy diagrams can look one of two ways. You either have your reactants are low in energy and your products are high in energy, which means that energy is absorbed in this case if the reactants have less energy than the products. And the reason why this is, if we assign a number to these, like let's say the reactants are, let's go with 5 again. And then let's say our products, let's say this point here is about, let's say that's 15. And then let's say this is the activation energy. Let's say that's up here at 25. Okay, so what I'm saying here is, remember, if you want to get delta H, you have to do the product's energy minus the reactant's energy. Okay, because that's what happened. You ended up with a certain amount of product that carries its own energy. But remember, the reactants also brought in their energy. So this is kind of like when you invest. If you're investing something, you're putting something into that overall mission. All right, so for example, when people invest money, they are putting in money and then they're getting out some amount of money. Okay, that is the overall net amount that they're going to make. Okay, so with energy, if my products have 15 kilojoules of energy, okay, and my reactants have 5 kilojoules of energy, okay, well 15 minus 5 is positive 10. Okay, so remember I told you guys if your enthalpy is positive, this is an endothermic reaction. And with an endothermic reaction, energy is absorbed. Okay? So if you notice that your products have higher energy than your reactants, look how my products have higher energy than my reactants, then you can bet that that's going to be an endothermic reaction. On the contrary, if your products have less energy than your reactants, then that's a red flag that it's going to be exothermic because your delta H will be negative. For example, let's say this product energy, let's say it's 2, okay? And then let's say my reactants energy is, 10. I'm just making up these numbers, but they're energy, they're kilojoules. Okay, so my delta H is products minus reactants. So if my products have 2 kilojoules of energy and my reactants have 10 kilojoules of energy, okay, well 2 minus 10 is negative 8 kilojoules. Okay, because this is negative, that is an exothermic reaction because heat was released, energy was released. Okay, so if your products have less energy, they're lower than your reactants, that is indicative of an exothermic reaction. Okay, so the delta H of a reaction is going to begin with the products as reactants. The reverse of the reaction begins with the products as the reactants and produces the reactants as products. Basically, it's the reverse, so it's a mirror image of this. So, for example, the reverse of this would be the reactants up here and then going like that. Okay, so I'm trying to mirror this. Okay, so my products become my reactants, and then my reactants energy becomes my products. Okay, if I were to do the reverse of this on the one on the right, so I would make my products my reactants and my reactants my products, so it would look like this. So my reactants would be here and my products would be here. Okay, so the reverse reaction. Okay, that's pretty much it on how to read an energy diagram for now. We can go a lot deeper, but for the basics, basically, an energy diagram shows you what's going on in a reaction. It starts off with the energy of your reactants and ends with the energy of the products. To get the overall energy that is formed in the reaction, you have to do the energy that the products are putting in minus the energy that the reactants are putting in. And then to determine the activation energy, that is the point from the reactants and then the highest point of the slope. Okay, so basically you would just have to find the difference.